right, we're back at it. Let's finish off this titration of the weak base and the strong acid. We just hit the halfway point in the titration, which fell in the buffer zone. Let's see what we get here. I want to redo those molarities right away. Doesn't really matter. Let's do the base first. I guess it comes first. Originally, I think they told us the base was 0.050 molar. We've got 100 milliliters. I need to know the new molarity when I join solutions, and my final volume becomes 150. M2. How about 0.033? I'm okay with that. Then we do the acid. Very similar. The acid starting at 0.1 molar. 50 milliliters is the original volume. We need to know the new molarity at 150. M2. La, 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 la. What do you know? It's the same. There's a word that might be popping in your head right now. Don't fight it. I think we might be at the equivalence point. Looks like we got equal moles of acid and base. We got to start out with this balanced equation. So again, it's the ammonia reacting with the hydrogen from the acid. Chlorine's a spectator, so we can leave them out. We're just going to form the NH4 ammonium plus 1 ion. We'll set up my ice table. These are starting out the same, 0.033, 0.033. Initially, no ammonium. So again, we react these as completely as possible. And now, if it didn't slap you in the face before, it probably is slapping you in the face at this moment. We are at the equivalence point. We have equal amounts of acid and base. So like if we react these as completely as possible, they're going down to 0. 0.033 down to 0, but we're going to form some of this ammonium ion, 0.033 moles per liter. So we could mark one thing in. This right here is the equivalence point. Equivalence point. The point where we have equal moles of acid and base, according to the balanced equation. Okay, now when this was the strong acid, strong base, it was great. You reacted all the hydrogen, you reacted all the hydroxide, all you had was water formed, so the pH was 7. With weak acids and bases, it stinks a little bit because you need another ice table. Or if you did this part in your head, maybe you could get away with one ice table. That's risky. I need to set up another one. I need to know, like, what's the pH of this solution? So basically what I have is an ammonium solution. What's the pH of a 0.033 molar ammonium solution? And I could at least kind of guess NH4, that should maybe be like a weak acid. That particle is weakly acidic. It could lose a hydrogen. So it might be something a little less than 7. I'm dying to find out. We need another ice table. So this time I need to start with my ammonium ion. What can it do? Well, it has a tendency to lose its hydrogen. Now, maybe I don't know. I don't want to get you too crazy. You can put water in if you want, or you can leave the water out. We're going to lose this extra hydrogen, so we'll be left with NH3. And that extra hydrogen will be attracted to water in the solution, which would become H3O, the hydronium ion, sign of an acid. That makes me excited. So, like, what we're going to form is a little bit of weak base, a particle that's weakly basic, and a particle that's more acidic. If you left water out, you would just have ammonia and hydrogen, and that would be totally acceptable. That would be totally fine. Let's do an ice table. The original ammonia is 0.033 molar. We're not going to care about the water, which is why it's fine if you do leave it out. I don't know. For weak acids and bases, I usually just put it in there. Then I don't have to worry about when I need it and when I don't. Initially, these products are 0, but they can't stay that way. So this is going to go down by x. 0, 3, 3 minus x. And these will go up by x. Excellent. All right. A little snafu here. We need to calculate x, and we're starting with the ammonium ion. Well, the only K value they ever gave us was the Kb for ammonia. We're using its conjugate acid. So just like in the last chapter, we need to find the Ka. We're using this particle in the acidic version. So we'd say Ka times Kb times 10 to the negative 5th equals Kw, or 10 to the negative 14th. So don't forget that little step. It was just like when we had, let's say it was an ammonium chloride solution or something like that. If we're using the conjugate acid, we need to calculate the Ka. So I've got Ka as about 5.56. Ooh, it's tiny. Times 10 to the negative 10th. That's x squared over 0.033 minus x. And again, there's no doubt we're going to 5% rule this thing. That K is small. So we plug this in our calculator. We'll cross multiply, take the square root. X equals. What are you feeling? Like 2 sig figs maybe? 4.3 times 10 to the negative 6. And again, of these two products, we've got some ammonia, and then we've got the hydronium ion, or maybe you just wrote it as hydrogen, which would have been 100% acceptable. This is the one that I really care about. This is the one that will have a greater effect on the overall pH of the solution. So we'll calculate pH based on hydronium. pH equals opposite log of 4.3 times 10 to the negative 6. You could have written H3O or just hydrogen, and I promise it would be acceptable. Let's call this maybe like, I don't know, 5.4-ish. Opposite log, 4.3 times 10 to the negative 6. Like 5.4 sounds good. That's kind of what I expected. I was thinking this would be a little bit acidic. And it is. If I go look back at my original ice table, when I reacted these two as completely as possible, I noticed right away that I was going to form the ammonium ion. And I knew that was slightly acidic. So this makes sense. And it kind of makes sense too. Like, they don't give us a graph to kind of compare. But if we are at the equivalence point of the titration between a strong acid and a weak base, again, like we have equal moles of acid and base, but it's kind of like the nature of the beast. This thing should still be slightly acidic. We're going to form a particle that is still slightly acidic. The last one in this section. This one won't be bad, I promise. Let's see what we got here. Recalculate the pH, or the molarities. Let's do that first. Base. It was 0.05 molar originally. 100 milliliters original. Eventually. There we go. 100 milliliters. We want to do the no molarity. After 60 milliliters of acid. Excellent. 160 total volume. M2. Oh, let's see. If we go like 2 sig figs maybe. How about 0.031? Yeah, that's good enough. And then I do the same thing with the acid. The acid. 0.1 originally. 60 milliliters. Whoopsie, 60 milliliters original volume. 60.0. I need to know the new molarity at 160. M2. How about 0.038? I like that. All right, so let's do our ice table here. We had the ammonia reacting with the hydrogen, forming the ammonium ion, NH4 plus 1. ICE. My original ammonia, my base, is 0.031. My acid is 0.038. And originally I don't have any ammonium. Oh, I can tell you're smiling right now. You like this one. We're going to react these as completely as possible. Our limiting reactant is the weak base this time. So you, my dear, are going down to 0. Everybody else reacts accordingly. This is going down by 0.031. Oh, this is nice. To 0.007 molar. And this is going to go up by 0.031 to 0.031 molar. Okay, so you might be grinning from ear to ear right now. I hope you are. We've got 2 particles remaining in the solution. We've got the acid, the hydrogen, and then we've got the ammonium. Well, this hydrogen is always a particle that's, see, that's a weird looking S, strongly acidic. This guy is weakly or mildly acidic. So, do I really care about the ammonium? Not really. Of these 2, the more important particle is this excess hydrogen. We've gone beyond the equivalence point now. So the solution is going to be relatively acidic. You don't have to try to figure out, okay, well, how much hydrogen is going to come when this thing redissociates. Who cares? It will be so insignificant compared to the amount of hydrogen in excess that any extra hydrogen that would come from this ammonium ion really won't have a significant effect on the overall pH. So I'm serious. You can really just go pH equals opposite log of that excess hydrogen. Molar hydrogen. Oh, I like that. We can plug it in our calculator. Opposite log 0.007. And we'll maybe say the pH is 2.2. Just what I expected. I figured that if we've gone far beyond the equivalence point, my remaining solution should be relatively acidic. And it is. So keep an eye out for that. At the end of a titration, if you have excess hydrogen or excess hydroxide, you can really just base the pH on that particle. Even if you have some weak acid or weak base, it will be insignificant to the overall pH. Base it on that hydrogen or hydroxide in excess. See, that wasn't so bad. Now I have another good news for you too. This next problem, this one about, what is it? Hydrogen cyanide being highly toxic. It's a weak acid. They're going to titrate it with sodium hydroxide. Skip it. We've already done one like this. This is a titration of a weak acid and a strong base, which we totally did before. We did the sodium hydroxide, and the weak acid was the acetic acid. So you don't have to worry about this hydrogen cyanide problem in the study guide. We have done all of that.